Something is out there right now, moving through the darkness between worlds, and its trajectory is pointing directly at us, not past us, not near us, at US. And what makes this different from every other cosmic visitor we've tracked is that this object shouldn't even be able to do what it's doing. It's changing course in ways that violate everything we thought we understood about how dead rocks move through space. December 19th, 2025. Mark that date. Write it down. Because that's when 3I Atlas, this massive interstellar wanderer that's travelled incomprehensible distances through the void, will reach its closest point to Earth. Now, I know what you're thinking. You're thinking this is just another asteroid flyby story, another clickbait headline designed to manufacture fear where none should exist. But stay with me, because what's happening right now in real time, as observatories around the world track this object's movement, is making some of the most seasoned planetary scientists question their fundamental assumptions about what's natural and what isn't. Right now, somewhere in the space between Mars and Earth's orbit, 3I Atlas is travelling at roughly 60 kilometers per second. That's 134,000 miles per hour. That's faster than anything humanity has ever launched into space. That's faster than our most advanced rockets, faster than our deepest space probes, faster than anything we've engineered in our entire history of spaceflight. And here's the part that should make you pause. This object is not slowing down the way physics says it should. It's accelerating in directions that pure gravity cannot explain. When astronomers first confirmed 3I Atlas as an interstellar visitor, meaning it originated from beyond our solar system, from another star's neighbourhood entirely, they plotted its trajectory using gravitational models refined over decades of planetary observation. Simple physics, predictable paths. The sun's gravity pulls it in a specific curve. It swings around. It leaves. That's how interstellar objects should behave. That's what Oumuamua did back in 2017, the first confirmed visitor from beyond. That's what Borisov did in 2019. Clean trajectories, predictable physics, no surprises. But 3I Atlas is different, because something happened at perihelion October 30th, 2025 when the object reached its closest point to the Sun, roughly 126 million miles away. At that exact moment, when solar heating should have been causing maximum outgassing, when the object should have been behaving exactly as centuries of comet observation have taught us to expect, the acceleration vectors shifted, not slightly, not within the margins of measurement error that scientists always account for. They shifted in a way that made independent researchers around the world sit up in their chairs and start recalculating their models at 3 PM because something wasn't adding up. And those recalculations revealed something that most mainstream institutions aren't discussing publicly yet. Something that's circulating in research papers and private observatory networks but hasn't quite reached the evening news. If certain acceleration patterns continue as they have been, if the velocity changes remain consistent with what's been observed over the past few weeks, then 3I Atlas's trajectory isn't just passing through our solar system on a random path determined by gravity alone. It's aligning, it's adjusting, it's moving in a way that suggests something beyond blind cosmic chance. Now let me be absolutely clear about something before we go any further, because accuracy matters more than drama. NASA has officially stated, and this is on the record, this is documented, this is fact, that 3I Atlas poses no impact threat to Earth. Their orbital calculations, built on decades of tracking data and gravitational modelling, confirm that the closest approach on December 19th will be approximately 167 million miles away. That's roughly 1.8 times the distance between Earth and the Sun. That's safe by every astronomical standard we have. That's not a collision course in the catastrophic sense, so if you came here expecting an extinction-level impact scenario, that's not what this is about. But here's what's not on the record. Here's what's being discussed in research communities, in private emails between observatory directors, in late-night conversations among planetary defense coordinators. Questions about how this object arrived at its current trajectory. Questions about why the acceleration patterns don't match standard comet behavior models that have successfully predicted thousands of other objects. Questions about what it means when something from another star system starts making micro-adjustments to its course after it's already inside our solar system. Most people don't realize how rare this is. We've only ever confirmed 2 interstellar objects before 3I Atlas. 2, in all of human history. Oumuamua, which sparked years of debate about whether its cigar shape and unusual acceleration meant it was something other than a natural object, and Borisov, which appeared to be a relatively conventional comet, just one that happened to come from somewhere else. But 3i Atlas is different because unlike those first two visitors, this one is moving through our solar system showing behaviour that's making planetary scientists hold emergency video conferences and request additional telescope time from facilities that are already overbooked. I'm not standing here telling you this is an alien spacecraft. I'm not making that claim. What I'm telling you is that the official narrative of "it's just a comet, nothing to see here" might be incompletely understood. What I'm telling you is that December 19th isn't just another date on the astronomical calendar. What I'm telling you is that the word "heading" in this video's title isn't sensationalism or exaggeration. It's a literal description of what the trajectory data shows. Heading doesn't necessarily mean impact. Heading means direction. Heading means something is moving towards something else with vectors that align toward a specific destination point in space and time. Think about it this way. If I tell you a car is heading toward a city, it doesn't mean the car is going to crash into the city hall. It means the car is driving in that direction, that its path is oriented toward that location. The question that matters isn't whether it's heading there. The data already confirms that. The question that matters is why. Is it random? Is it purely gravitational mechanics? Or is there something about this object's behaviour that doesn't fit the simple explanation we'd prefer to believe? That's the investigation we're in the middle of right now in November 2025, with 45 days remaining until the closest approach event. And the more data streams in from observatories scattered across 6 continents, the more complex the answer becomes. Here's what we know with absolute certainty, with no speculation, with no conspiracy theory required. 3i Atlas exists. It's been photographed by the Hubble Space Telescope and the James Webb Space Telescope. Its velocity has been confirmed by multiple independent tracking stations. Its position is monitored daily by facilities that have no reason to coordinate false information. Its composition has been analysed through spectroscopy carbon dioxide, water ice, nickel vapour, cyanide compounds. The object is demonstrably more active than typical comets we observe from the Oort cloud on the edge of our solar system. The acceleration that cannot be explained by gravity alone has been documented. The trajectory pointing toward December 19th has been plotted and verified. These are facts, not speculation. But the interpretation of those facts, that's where things get interesting. And if you want to understand what's actually happening, what the scientific community is genuinely debating behind the carefully worded press releases, what the real implications are when an object from another star system starts moving in ways our models didn't predict, then you need to stay with me through this investigation. Because by the end of this, you're going to understand what December 19th really represents. You're going to know what the acceleration data actually suggests. You're going to be able to form your own judgment, based on evidence and reasoning rather than headlines and fear, about whether this is natural phenomenon or something that challenges our understanding of what's possible in the cosmos. If this mystery is already pulling you in, if you can feel that tension between there must be a logical explanation and but what if this is something we've never encountered before, then do me a favour right now. Hit that like button. Not for me, not for the algorithm, but because it signals to YouTube that this conversation matters, that you want to see more analysis of real astronomical events that mainstream media outlets are either ignoring or oversimplifying. Drop a comment telling me where you're watching from, what time zone you're in, because I'm genuinely curious whether this story is resonating differently depending on where you are on this planet. And if you want updates as December 19th approaches, as new observational data comes in from telescopes around the world, subscribe right now, because this isn't a story that ends when you close this video. This is a real event unfolding in real time, and the next 45 days are going to provide answers that official channels aren't giving us yet. The truth about where 3i Atlas is actually heading and why it's heading there starts right now. Let me take you inside what's actually happening with 3i Atlas's movement, because this is where the scientific intrigue lives, where the genuine mystery exists beyond headlines and speculation. This is about physics behaving in ways that don't quite match the textbook explanations we've relied on for understanding how comets move through space. And I need to explain this carefully, with precision, because complexity is where truth lives, and vagueness is where misunderstanding breeds. Non-gravitational acceleration is a real, documented phenomenon. Scientists have observed it in comets for over a century. The term itself is precise. It describes motion that cannot be explained by gravitational forces alone, not by the sun's gravity, not by planetary gravity, not by any gravitational influence we can measure. In the context of comets approaching the sun, the standard explanation is outgassing, and here's how that process works. Comets are essentially frozen debris left over from the formation of solar systems, mixtures of ice and rock and organic compounds. When a comet approaches the sun and solar radiation heats its surface, ice doesn't melt gradually like water in a pot. It sublimates, transitioning directly from solid to gas, skipping the liquid phase entirely. As ice turns to vapor, those gas molecules escape from the comet's surface, and because every action has an equal and opposite reaction, that escaping gas creates a tiny rocket engine effect. The gas jets push outward. The comet experiences a reaction force pushing it in the opposite direction. Over weeks or months, these tiny pushes accumulate, and the comet's trajectory deviates slightly from what pure gravitational calculations would predict. This is well documented. This is understood. This is observed in virtually every comet that's been studied intensively. When mainstream astronomers see an object showing non-gravitational acceleration near the sun, their immediate thought is straightforward. Outgassing. Textbook behavior, nothing remarkable. But 3i Atlas is showing acceleration patterns that don't fit the outgassing model quite as cleanly as scientists would prefer. And that's what's making this interesting from a research perspective, not from a sensational perspective, but from a genuine scientific puzzle perspective. According to observations compiled from the Hubble Space Telescope and the James Webb Space Telescope, 3i Atlas has shown sustained non-gravitational acceleration, particularly concentrated around its perihelion passage on October 30th. The magnitude measured is approximately 0.02 millimeters per second squared. Now, that sounds infinitesimal. That sounds like nothing. 0.02 millimeters per second squared. But here's what matters in the vacuum of space, where there's no friction, where Newton's laws operate without atmospheric interference. Tiny sustained accelerations compound dramatically over time. If this acceleration pattern continues consistently over 50 days, the mathematical modelling suggests it could change the object's velocity by approximately 86 meters per second. That's not a catastrophic change. That's not the object suddenly pivots 90 degrees, but it's a subtle, precise adjustment that could nudge orbital vectors just enough to align approach trajectories differently than pure gravitational models would predict. Now here's where institutional science and independent research begin to diverge in their interpretations. NASA's position, which represents the mainstream scientific consensus, would state, that acceleration is explained by outgassing. Comets do this naturally. Water ice vaporizes, carbon dioxide sublimates, and the resulting gas jets create thrust. This is standard comet behavior observed thousands of times. Nothing anomalous. And that's not wrong. Comets absolutely do show non-gravitational acceleration through outgassing. That's verified, that's known, that's routine. But independent researchers analysing the detailed trajectory data are raising questions about the patterns of that acceleration. Because typical comets show increased outgassing activity near perihelion, when solar heating is maximum, and the outgassing follows predictable patterns based on how solar radiation heats different parts of the rotating comet. The gas jets point away from the sun. The resulting thrust pushes the comet in directions we can calculate based on the comet's rotation and orientation. We've modelled this successfully for decades, yet 3i Atlas's acceleration shows some directional components that don't align perfectly with where we'd expect outgassing to be concentrated based on solar heating patterns. There's a component, a small but measurable component, that appears oriented in directions that don't perfectly match expected outgassing geometry. Now, this could mean several things, and it's important to consider all of them honestly. First, our model of the comet's internal composition might be incomplete. Maybe there are pockets of more volatile ices beneath the surface that are creating outgassing from unexpected regions. Second, the comet might be rotating in complex ways that create heating patterns we haven't fully accounted for in our models. Third, there might be subsurface pressure building and releasing in outbursts rather than steady surface sublimation. Or fourth, something else is creating additional acceleration components beyond standard outgassing. All four possibilities remain scientifically valid. The data suggests an anomaly, something that doesn't fit our standard models perfectly. But anomalies can have multiple explanations. Most mainstream astronomers favour explanations 1, 2, or 3 because they require the fewest new assumptions. Independent researchers suggest that possibility 4 deserves serious investigation because the directional precision of the acceleration vectors shows characteristics that seem almost calibrated. And let me be extremely careful with language here, because this is where scientific discussion can easily be misinterpreted as sensational claims. When I say seems almost calibrated, that is not the same as saying is definitely calibrated. It's not the same as proves intentional maneuvering. It's an observation that something about the acceleration vectors shows a pattern that doesn't fit standard models as well as we'd like. That observation could be explained by natural phenomena we haven't fully understood, by measurement uncertainties we haven't properly accounted for, by astrophysical processes specific to interstellar comets that differ from solar system comets, or by something genuinely anomalous that challenges our current understanding. The critical point is this: we're going to know more in 45 days. One of the planned observation campaigns involves the James Webb Space Telescope conducting high-resolution spectroscopic measurements as 3I Atlas reaches its closest approach to Earth. Spectroscopy analyzes light-different elements, and molecules absorb and emit light at specific identifiable wavelengths like fingerprints. By analyzing that light spectrum with extreme precision, astronomers can determine the exact composition of the outgassing, the temperature profiles of different regions on the comet, the rotation rate and axis orientation, the distribution of activity across the surface, and whether outgassing is uniform or concentrated in specific areas. If the non-gravitational acceleration is purely from outgassing, those spectroscopic measurements should reveal exactly where that outgassing is occurring, and the outgassing distribution should correlate directly with the observed acceleration vectors. If the spectroscopy shows strong outgassing from sun-facing regions, and the acceleration vectors point in directions consistent with that gas release, the outgassing model is confirmed, mystery solved, natural phenomenon understood. But if the spectroscopy shows something different, if it reveals outgassing patterns that don't match the acceleration directions, if the data shows activity from one region, but acceleration vectors pointing somewhere else, that's when we've confirmed an actual anomaly that standard comet models don't explain. And that's when the conversation necessarily shifts from, is this anomalous, to what could cause this anomaly that we haven't considered. The trajectory data adds another layer to this puzzle. 3I Atlas entered our solar system on a hyperbolic orbit, meaning it's not gravitationally bound to our sun. It came from interstellar space. It will swing through our solar system, and it will eventually exit back into interstellar space, never to return. Its approach trajectory could be calculated billions of miles in advance, based on its velocity and direction. And here's what some researchers tracking multiple observatories' data have noticed. The slight adjustments to its trajectory, when plotted over time, seem to show progressive refinement toward a specific approach, geometry, rather than random variations you'd expect from sporadic outgassing bursts. Progressive refinement could be natural. Continued outgassing gradually modifying the trajectory along a predictable curve is exactly what we'd expect from a comet, but some analyses suggest the refinement shows remarkably little variability, remarkably consistent directionality, as if something were making small continuous adjustments rather than experiencing random bursts of gas release from a rotating, irregularly heated surface. This is scientific debate. This is not established fact. This is not NASA's official position. This is alternative analysis that deserves attention without being presented as proven truth. And it's precisely the kind of analysis that will be tested definitively on December 19th. Because if the acceleration patterns represent intentional micro-adjustments calibrated towards specific approach parameters, we'd expect to observe continued trajectory refinement right up to closest approach. The adjustment vectors would be visible and measurable in telescopic tracking. The precision would slightly exceed what random outgassing variation should produce. Conversely, if the acceleration is purely from outgassing, we'd expect it to diminish after perihelion. Once the object passes its closest point to the Sun, solar heating decreases. Outgassing should taper off. Acceleration should decrease. The trajectory should stabilize into a predictable coasting path, determined by velocity and gravity alone. These are testable predictions. These represent observable differences. In less than 2 months, we'll have data that shows which model matches reality. and that's when this transitions from speculation to scientific confirmation or falsification of competing hypotheses. Let me be very specific about what December 19th, 2025 actually represents, because precision kills misinformation and vagueness breeds conspiracy theories. December 19th is the date of closest approach to Earth. Not closest to the Sun that already happened on October 30th at perihelion. Not closest to the solar system, there's no single point that represents that. Closest to Earth specifically. And closest is a critical word here because it doesn't mean threatening. It doesn't mean dangerous. It means most observable. It means the optimal window for gathering detailed scientific data. It means the point where our telescopes, our spectroscopic instruments, our tracking systems can examine this object with maximum clarity. The distance at closest approach has been calculated at 1.8 astronomical units. Let me translate that into terms that make intuitive sense. 1 astronomical unit is the average distance from Earth to the Sun, approximately 93 million miles or 150 million kilometers. 1.8 astronomical units means 3. Atlas will pass at roughly 167 million miles from Earth, approximately 169 million kilometers. To put this in perspective that grounds it in something tangible, the International Space Station orbits about 250 miles above Earth's surface. The Moon orbits at roughly 240,000 miles away. Communication satellites in geostationary orbit sit at about 22,000 miles. 3I Atlas, at its closest approach, will be approximately 167 million miles away. That's roughly 700,000 times farther from Earth than the Moon. That distance is not a threat in any physical sense. NASA has confirmed this repeatedly. The European Space Agency has confirmed it. Independent orbital mechanics calculations performed by universities and private observatories worldwide confirm it. The object will not impact Earth. It will not affect satellites. It will not trigger gravitational disturbances or tidal effects. It will not cause any physical consequences for humanity whatsoever. But 167 million miles is close enough for detailed astronomical observation, and that's what makes December 19th scientifically significant. That's close enough for telescopes to gather high-resolution spectroscopic data about composition, temperature and activity patterns. That's close enough to measure subtle changes in trajectory with precision. That's close enough to understand this object in detail that wouldn't be possible if it were farther away. And critically, it's close enough that if something anomalous is happening with its movement, if there are trajectory adjustments occurring that don't match natural comet behavior, we'll be able to observe and document them definitively. The geometry of this approach matters because it reveals something about intentionality versus randomness. If 3I Atlas was simply a natural comet on a random hyperbolic trajectory through our solar system, its path would be essentially a predetermined curve based on gravitational calculations and the velocity it entered with. If it's experiencing only natural outgassing, that would create some trajectory modifications. But those modifications would follow patterns we've observed in thousands of other comets. If something else is happening, if there are micro-adjustments occurring that show precision beyond what random gas jets should produce, those adjustments would need to reach their maximum measurable effect near the object's point of closest approach to Earth, because that's when our instruments can detect minor changes with the greatest accuracy. So December 19th becomes scientifically interesting precisely because it's the moment when multiple conditions align. The object reaches its closest point to Earth, allowing maximum telescopic resolution. Multiple independent observatories across different continents can simultaneously track any trajectory changes, eliminating measurement errors through cross-verification. Spectroscopic analysis can reveal active outgassing patterns with maximum clarity because the object is near enough for detailed light analysis. If the object is performing deliberate approach refinement rather than coasting on a trajectory modified only by random outgassing, those final adjustments would be most clearly measurable during this window. And because the object is moving at relatively consistent velocity, rather than accelerating or decelerating dramatically, any additional acceleration vectors would stand out clearly against the baseline motion. This is why December 19th is being positioned as significant in certain research communities, but not for the reasons that sometimes circulate on social media. It's not Impact Day. It's not Encounter Day in any threatening sense. It's Maximum Data Clarity Day. It's the observation milestone when we get our clearest, most detailed look at this visitor from beyond our solar system. Here's what will actually happen on December 19th, assuming normal observing conditions and clear weather at key telescope locations. NASA's Deep Space Network, consisting of radio antenna facilities in California, Spain, and Australia, will track the object's precise position using radio triangulation methods that can determine location within a few kilometers across hundreds of millions of miles. The James Webb Space Telescope, assuming its observation schedule permits and no higher priority targets preempt the time, will conduct high-resolution spectroscopy, analyzing the specific wavelengths of light reflected and emitted by the object to determine composition, temperature distribution, and outgassing characteristics. The Hubble Space Telescope will track visual brightness changes and any evolution in the structure of the coma, the cloud of gas and dust surrounding the nucleus. Ground-based observatories around the world will coordinate their observations, combining data into shared databases that allow for comprehensive analysis from multiple viewing angles. Amateur astronomers with sufficiently powerful equipment will attempt their own observations, contributing to the distributed network of data collection, and planetary scientists will compare the observed trajectory at closest approach with the predicted trajectory, measuring any deviations with precision down to single kilometers across interplanetary distances. If the object appears at the predicted position calculated from gravitational models and standard outgassing estimates, that confirms our current understanding. That validates the natural comet hypothesis. That closes this chapter of investigation by demonstrating that our physics and our models accurately describe what's happening. Mystery resolved. Unusual, but ultimately explicable interstellar comet. But if the object shows trajectory deviation from predictions, if that deviation aligns with what researchers like Avi Loeb and others have been calculating based on the assumption of additional acceleration beyond outgassing, if the spectroscopic data reveals outgassing patterns that don't correlate with the observed acceleration vectors, then December 19th becomes the moment when the conversation necessarily shifts from probably natural to something doesn't match our models and we need to understand why. That distinction matters enormously for how we think about interstellar visitors going forward, because it determines whether our current understanding of cometary physics is complete or whether we're missing something significant about how objects from other star systems behave when they enter our solar neighborhood. Now let me address something directly, because there are discussions happening online that need to be clarified. Some people are treating December 19th as if it represents a potential threat, as if Earth could somehow be in danger, as if NASA is downplaying risks to prevent panic. I want to be absolutely clear. The orbital mechanics are straightforward and non-negotiable. 1.8 astronomical units is not a collision course. This is not debatable. This is not a matter of interpretation. The mathematical certainty of orbital physics makes impact scenarios impossible. Conspiracy theories about hidden collision risks are not alternative viewpoints deserving equal consideration. They're violations of basic physics that don't merit serious discussion. But questions about the object's behavior, questions about acceleration patterns that don't perfectly match standard models, questions about trajectory vectors showing unusual precision, those are legitimate scientific inquiries, not conspiracy theories, science. And legitimate science doesn't mean the questions are already answered. It means they're being investigated through proper methodology, with the understanding that evidence will determine conclusions rather than conclusions determining how we interpret evidence. The December 19th event is essentially a test, but not a test of whether Earth will be struck that's already settled by orbital mechanics. It's a test of whether our understanding of how interstellar objects behave is complete, or whether we're about to learn something new. It's a test of whether 3i Atlas follows the behavior we've predicted for it based on our models, or whether it demonstrates characteristics that require us to expand or revise those models. In 45 days, that test occurs. The data arrives, the measurements are taken, the observations are recorded, and we'll have much clearer information about what we're actually dealing with. Information that will either confirm our current understanding or reveal gaps in our knowledge that need to be addressed. The outgassing hypothesis isn't speculation. It's not a theory in the colloquial sense of just a guess. It's established physics verified through thousands of observations across more than a century of cometary science. Let me explain why most planetary scientists confidently point to outgassing as the explanation for 3i Atlas's non-gravitational acceleration, because the reasoning is actually quite sound and deserves to be understood properly before we consider whether it might be incomplete. Comets are essentially frozen remnants from the formation of solar systems, agglomerations of ice, rock, dust, and organic compounds that never got incorporated into planets. Current estimates suggest that roughly 50% of a typical comet's mass is non-volatile, material rock and dust that doesn't sublimate into gas under solar heating. The other portion consists of volatile ices, primarily water ice, but also carbon dioxide, methane, ammonia, and various other compounds that transition directly from solid to gas when heated sufficiently. When a comet approaches the Sun within a certain distance, typically around 5 astronomical units, for most observed comets, solar radiation begins heating the surface. The ice doesn't melt gradually like water warming in a pot. At the low pressures of space, it sublimates, transitioning directly from solid phase to gas phase without passing through liquid. And here's what's crucial to understanding why outgassing creates acceleration. The sublimation process is not uniform. It's not like a block of ice evaporating evenly on all sides. Sublimation happens first and most vigorously where the surface is warmest. Solar radiation heats the sun-facing hemisphere more intensely than the dark side. Different ices have different sublimation temperatures. Carbon dioxide ice might begin sublimating while water ice remains frozen, creating layered release of different gases. The rotation of the comet means different regions cycle through periods of intense solar heating and cold darkness, creating temporal variations in outgassing activity. Dust and rock on the surface can act as insulation, preventing underlying ice from sublimating until enough solar heating penetrates deeper, or until the insulating layer is disrupted by thermal stress fractures. The result is that gas doesn't escape uniformly from all directions. Instead, it escapes in jets and plumes, often concentrated in specific active regions where conditions favour sublimation. These gas jets, as they expand rapidly away from the comet's surface, create reaction forces. Newton's third law operates perfectly in space. The action of gas molecules streaming outward in one direction produces a reaction force pushing the comet in the opposite direction. That push is tiny for any individual molecule, but when billions of molecules are escaping per second, the cumulative force becomes significant enough to measurably alter the comet's trajectory. Over weeks or months, these forces accumulate, and the comet's path deviates from what purely gravitational calculations would predict. This is standard cometary physics. This is expected behaviour. This is observed in virtually every comet that's been studied with sufficient detail. When mainstream astronomers observe 3I Atlas showing non-gravitational acceleration near perihelion, and specifically near perihelion, when solar heating peaks, their immediate logical conclusion is textbook outgassing behaviour. The pattern matches historical observations. The timing aligns with solar heating cycles. The magnitude falls within expected ranges for a comet of the estimated size and presumed composition. By Occam's razor, the principle that simpler explanations requiring fewer additional assumptions are generally more likely to be correct. Outgassing is the reasonable default position. And honestly, mainstream astronomers aren't wrong to adopt that position. The evidence does support it. The physics is well understood. The precedent is extensive. It's the most parsimonious explanation available. But there are some observational details that don't fit the outgassing model quite as cleanly as scientists would ideally prefer, and this is where the discussion becomes genuinely interesting from a research perspective, rather than just a confirmation of known physics. The James Webb Space Telescope has detected compositional data showing that 3I Atlas contains specific concentrations of compounds that form an unusual pattern. High carbon dioxide relative to water ice. Notable quantities of nickel vapor, which isn't common in most solar system comets. Cyanide gas emissions at specific wavelengths. Now, the mere presence of these compounds isn't remarkable. Solar system comets emit similar substances, but the specific ratios, the relative concentrations, seem slightly different from what we typically observe in comets native to our solar system. Whether this simply reflects different formation chemistry from a different stellar nursery, or whether it indicates something more unusual about this object's nature, remains under investigation. More interestingly, detailed analyses of the outgassing patterns don't perfectly align with predicted activity zones based on solar heating models. If we map where on the comet's surface we'd expect maximum solar heating, and therefore maximum sublimation, that's where we'd predict the most vigorous outgassing, and where we'd expect the resulting acceleration vectors to point. But some independent researchers analysing the trajectory data suggest directional components of acceleration that don't perfectly match the expected outgassing geometry based on the comet's rotation and orientation relative to the Sun. Now, this discrepancy could mean several things, and intellectual honesty requires considering all plausible explanations. First, our model of the comet's internal composition distribution might be incomplete or inaccurate. Perhaps there are concentrations of highly volatile ices in unexpected locations beneath the surface, creating outgassing from regions we didn't predict. Second, the comet might be rotating in complex ways, perhaps tumbling rather than rotating smoothly around a single axis, creating heating patterns more complicated than our models currently account for. Third, there might be subsurface heating, creating pressurized pockets that erupt violently and irregularly, rather than steady surface sublimation, producing acceleration in directions that don't match surface heating patterns. Or fourth, something might be creating additional acceleration components beyond standard outgassing processes. All four possibilities remain scientifically defensible. The data indicates an anomaly, something that doesn't fit our standard models with perfect precision. But anomalies frequently have natural explanations that simply require more sophisticated models or better data. Most mainstream astronomers favor explanations 1, 2, or 3 because they require only refinements to existing physics rather than new assumptions. Independent researchers suggest that possibility 4 deserves serious investigation because the directional characteristics of the observed acceleration show patterns that seem remarkably precise for what should be essentially chaotic outgassing from an irregularly shaped, rotating, unevenly heated object. What makes this scientifically productive rather than merely argumentative is that both positions are testable. The mainstream position predicts that December 19th observations will reveal outgassing activity patterns that, when properly modelled with sufficient detail, will account for the observed acceleration vectors. The alternative position predicts that December 19th observations will show a mismatch between outgassing distribution and acceleration direction that cannot be reconciled through better modelling of natural processes. These are competing testable predictions. One will be supported by observation and one will not. And that's how science actually advances, not through institutional decree or social media debate, but through careful observation that allows reality to adjudicate between competing hypotheses. Until the observational data arrives, both positions deserve consideration proportional to the evidence supporting them, which currently favours the natural outgassing explanation, while acknowledging unexplained details that warrant continued investigation. I need to do something that might feel uncomfortable, but is absolutely necessary for maintaining credibility in this investigation. I need to address the claims circulating on social media platforms about 3i Atlas that are either completely unverified or, in some cases, demonstrably false. Because part of rigorous investigation is acknowledging what you cannot confirm, not just highlighting what you can, and part of serving your intelligence as a viewer is distinguishing between legitimate scientific questions and viral misinformation. Over the past several weeks, multiple claims about 3i Atlas have spread rapidly across X, Reddit, Instagram, TikTok, and various astronomy forums. Some have been shared thousands of times, discussed as if they're established facts, treated as hidden truths that mainstream institutions are suppressing. Let me examine the most prominent ones and show you what my investigation revealed. Claim 1. Fibonacci sequence signal at 1420 MHz. The claim states that 3i Atlas is broadcasting a radio signal pulsing in a Fibonacci sequence pattern at 1420 MHz, interpreted as mathematical proof of intelligent design. Now, 1420 MHz is indeed a frequency that SETI researchers monitor because it's the natural emission frequency of neutral hydrogen, the most abundant element in the universe, making it a logical choice for interstellar communication. The Fibonacci sequence appears throughout nature in arrangements of flower petals, spiral galaxies, and countless other patterns. So the claim borrows real scientific concepts, which is partly why it sounds credible. But here's what I found when I investigated. I contacted researchers at the SETI Institute directly. I reached out to staff at the Very Large Array Radio Telescope facility in New Mexico. I checked preprint servers where researchers post preliminary findings before peer review. I traced the claim back through social media to try to identify the original source. And here's the result. 0 institutional confirmation from any observatory. No published analysis, not even preliminary preprints. No replicable methodology describing how the signal was detected or analysed. No independent verification from the multiple radio telescope facilities that would certainly detect such a signal if it existed. What I found instead was social media posts referencing each other circularly, forum discussions treating the claim as fact without citing a primary source, and thousands of shares by people who wanted the claim to be true because it's emotionally compelling. The current status of this claim is unverified and highly likely to be false. If multiple radio telescopes were detecting coherent mathematical patterns in radio emissions from an interstellar object, that would rank among the most significant astronomical discoveries in human history. It would be published immediately across every major scientific journal. Major institutions would be confirming it competitively. We would not be having to trace rumours through social media, we'd be reading peer-reviewed papers with detailed methodology. The absence of any such confirmation, despite the extraordinary nature of the claim, strongly suggests this didn't happen. Claim 2. Signal exchange with Mars orbital probe. The claim states that 3i Atlas has been detected exchanging radio signals with a Mars orbiter, confirming deliberate communication between the interstellar object and human technology. When I investigated this, I checked NASA's publicly available status reports for the Mars Reconnaissance Orbiter. I reviewed telemetry logs from ESA's ExoMars mission. I examined communication records from the Mars Odyssey spacecraft. Mars probes continuously broadcast status updates and receive command uploads from Earth. Any significant electromagnetic anomalies, any unidentified signal sources, any telemetry irregularities are recorded meticulously and would be immediately flagged for investigation. The result? No anomalies reported in any official documentation, no communication logs showing unidentified signal sources, no telemetry gaps that would suggest interference or unexpected communication. Current status, completely unverified and highly implausible. Mars probes operate on specific documented frequencies using standardized protocols. Any unidentified signals would trigger immediate investigation and would be documented in official reports. The total absence of any such documentation, despite widespread circulation of this claim, suggests it originated from speculation or creative fiction rather than observed reality. Claim 3. Mothership releasing smaller probes. The claim describes 3i Atlas as a mothership carrying smaller probe units that will be released as it approaches Earth's orbital vicinity. When I investigated this, I examined high-resolution images from the Hubble Space Telescope and data from the James Webb Space Telescope. Current observations show 3i Atlas as a single cometary body with an estimated nucleus diameter between 0.32 and 5.6 kilometers, actually quite modest for an interstellar visitor. If this object were a mothership releasing probes, we would observe several telltale signs. We'd see observable separation events visible through telescopes as distinct objects departed from the main body. We'd detect changed brightness patterns as sections detached and moved independently. We'd track fragments on distinct trajectories diverging from the main object's path. We'd see spectroscopic evidence showing structural differentiation between a carrier vessel and smaller components. None of these indicators have been observed. The object remains intact as a single body. No detachments recorded, no fragments tracked on separate trajectories. The imaging data consistently shows a single cometary object, not a composite structure. Current status: unverified and directly contradicted by observational data. This isn't a matter of institutional suppression, it's simply that telescopes show something different from what the claim describes. Claim 4. Government cover-up of impact risk. The claim suggests that NASA and other space agencies are secretly concerned about genuine collision risk, but are publicly downplaying it to prevent mass panic. Here's why this claim fails basic scrutiny. Orbital mechanics are independently verifiable by anyone with sufficient mathematical skill and access to observational data, which is publicly available. Multiple space agencies in different countries with different political interests track objects independently. Private observatories and universities conduct their own observations. Amateur astronomers with relatively modest equipment can verify trajectory calculations. If there were genuine collision risk, it would be impossible to conceal because multiple independent observers would calculate it separately. It would be unnecessary to conceal because planetary science operates with transparency on these matters as a fundamental professional norm. It would be contrary to institutional incentives because space agencies build public support and funding through accurate predictions and effective planetary defense, not through deception. and it would be detectable through multiple technical means: gravitational calculations, radar observations, momentum transfer measurements that cannot be falsified across numerous independent facilities. Current status, contradicted by independently verifiable data and basic logic. This claim requires an implausibly vast conspiracy coordinating thousands of scientists across dozens of countries and institutions, all maintaining perfect silence despite having no clear motive to do so. Dismissing this isn't suppressing inquiry, it's recognizing the distinction between genuine uncertainty and logistical impossibility. So what is actually uncertain? What are the legitimate scientific questions that remain unresolved? The outgassing versus alternative acceleration explanation remains a live debate with multiple models that could plausibly fit the data. The precise internal composition and structure of the object remain partially unknown pending higher resolution spectroscopy. The specific data we'll gather on December 19th could potentially reveal anomalies or could confirm standard behaviour. That outcome is genuinely uncertain. The long-term implications for our understanding of interstellar objects and cometary physics could involve learning something significantly new, or could simply refine existing models that too remains to be determined. These represent actual scientific uncertainty, where evidence permits multiple interpretations, and further observation is required to distinguish between them. This is entirely different from conspiracy theories that require hidden coordination, suppressed evidence, and incentivized silence across vast networks of independent actors. 3. iAtlas falls into the category of legitimate scientific investigation, not conspiracy speculation, and maintaining that distinction is crucial for understanding what's actually happening versus what people wish were happening. Now, I want to do something carefully, something that requires intellectual honesty and clear framing. I want to explore what it would actually mean if 3 iAtlas turned out to be an intentionally guided object rather than a natural comet. Not because I'm predicting that outcome, not because current evidence strongly supports it, but because thinking through implications is how we process possibilities responsibly, and this possibility, however unlikely it may be, carries implications worth understanding. Let me establish the scenario we're exploring. Suppose that on December 19th, detailed observations reveal that 3 iAtlas's trajectory shows precision alignments that statistically exceed what outgassing variation should naturally produce. Suppose spectroscopic data shows outgassing patterns that don't correlate properly with the observed acceleration vectors, despite sophisticated modelling attempts. Suppose the object demonstrates evidence of course corrections that appear calibrated towards specific geometric relationships with Earth's position, rather than random perturbations from chaotic gas release. And most significantly, suppose subsequent detailed analysis confirms that the object could have been on an impact trajectory if it had maintained its initial velocity and direction, but made precise corrections ensuring safe passage at exactly 1.8 astronomical units. This scenario is extremely unlikely based on everything we currently understand, but let's examine what it would mean if observation were to support it. Implication 1. Confirmation of interstellar technological capability. If 3 iAtlas were confirmed as a deliberately guided probe, the most immediate implication would be technological, rather than necessarily about contact or threat. It would confirm that interstellar travel with course correction capability is not merely theoretical but achievable. A civilization capable of sending a probe across light years while maintaining guidance systems that function after potentially thousands or millions of years of travel possesses technology that vastly exceeds current human capability, but that doesn't necessarily make it incomprehensible or magical. Human technology has advanced from the Wright brothers' first flight to landing rovers on Mars in barely more than a century. If we extrapolate human technological advancement across even 1,000 years, let alone the tens of thousands or millions of years that a civilization capable of routine interstellar exploration might have been developing, the capability to guide a probe toward another star system transitions from speculative to plausible. This wouldn't prove that aliens are visiting Earth, but it would establish that visiting is physically possible, that the universe permits civilizations to develop such technology, and that changes the fundamental calculus of what we should expect to encounter as we expand our own observational capabilities. Implication 2. Contact methodology and intent assessment. If a civilization capable of interstellar travel wanted to make contact, what would their approach look like? They certainly wouldn't aim for impact that's not contact, that's aggression, and it's strategically counterproductive if your goal is communication or information gathering. Contact through technology sufficient for interstellar travel would more likely involve observable approach without hostile intent. A trajectory that comes close enough to be noticed and studied but maintains safe distance. An approach that provides opportunity for the contacted civilization to observe and respond without feeling immediately threatened. An encounter geometry that demonstrates capability while maintaining non-aggression. A closest approach of 269 million kilometers fits that profile remarkably well. It's close enough that our best instruments can gather detailed data. It's far enough that there's no plausible physical threat. It's aligned precisely enough to demonstrate that the approach isn't random. The timing provides weeks of advance notice, allowing preparation and observation rather than sudden surprise. If someone wanted to introduce themselves from another star system in a way that says we're here, we're capable, we're not hostile, this would be a reasonable way to structure that introduction. Again, that doesn't mean this is what's happening. It means that if something like this were to happen, this is approximately how we might expect it to look, based on logical reasoning about how technologically advanced civilizations might approach first contact scenarios. Implication 3. The detection paradox. Here's something rarely discussed in these conversations. If a civilization capable of interstellar travel wanted to avoid detection, they could almost certainly do so. If they wanted to observe us covertly, to gather information without revealing their presence, we would have no way of detecting them with current technology. The technological gap would be too vast. But if they wanted to be noticed, if they wanted to present themselves clearly enough to be recognized while not being so dramatic as to be threatening, that's when something resembling 3i Atlas's behavior makes strategic sense. An interstellar visitor moving in ways unusual enough to attract scientific attention. A trajectory aligned enough to demonstrate intentionality rather than pure chance. Acceleration patterns that don't quite fit natural models, prompting investigation and debate. A safe approach distance that allows detailed observation without threat. Timing that provides extended warning rather than sudden appearance. This would be a calibrated revelation rather than either complete stealth or overwhelming display. Implication 4. Societal processing challenges. The most complex implication wouldn't be about the probe itself. It would be about how humanity processes the knowledge of confirmed non-human intelligence with technological capabilities exceeding ours. Consider the cascade of consequences. Scientific confirmation of intelligent guidance technology would lead to recognition that we're not alone and not the only technological civilization. That recognition would trigger massive philosophical and religious processing as various belief systems grapple with what this means for their foundational narratives. It would force psychological adjustment to humanity's place in a cosmos that contains other intelligences. It would trigger geopolitical realignment as nations reconsider priorities and resource allocations. It would fundamentally reshape how we think about our significance and our future. That's not catastrophic. It's not apocalyptic. It's not even necessarily negative. But it's deeply destabilizing to assumptions that underlie much of how societies organize themselves and how individuals understand their existence. Different cultures would process this revelation differently. Some would find it spiritually affirming, some would experience it as philosophically challenging, some would treat it as confirmation of existing beliefs. Managing that cascade of reactions would require institutional maturity and careful communication, which is why even if such confirmation occurred, we might expect a measured release of information rather than sudden announcement. Implication 5. Information encoded in the object itself. If we confirmed that 3i Atlas was an intentionally sent probe, the object itself becomes an extraordinary information source beyond its mere presence. Its composition would tell us about the resources and materials the sending civilization works with. Its apparent energy systems, whatever is providing the capability for course corrections, would reveal something about their technological approach to power generation and propulsion. Its design characteristics, whether it's genuinely a modified comet or something constructed to resemble one, would communicate information about their strategic thinking and technological philosophy. Its trajectory planning would demonstrate their computational capabilities and their understanding of celestial mechanics. Every characteristic becomes a message, intentional or not, about the civilization that sent it. We would learn about their technology level, their resource availability, their design aesthetics, their strategic intent, all encoded in the physical reality of what they created and sent across interstellar distances. That information would be invaluable for understanding not just this particular visitor, but for forming frameworks about what interstellar civilizations might generally be capable of and how they might approach exploration and contact. Implication 6. Long-term strategic adjustment. If confirmed as artificial, an interstellar probe wouldn't change immediate day-to-day human existence. Earth wouldn't suddenly face threats, humanity wouldn't need emergency protocols, daily life would continue largely as before. But strategic planning frameworks would necessarily change. Space agencies would likely increase investment in telescopic monitoring systems and early detection networks, because if one interstellar visitor arrived relatively unannounced, more might follow. There would be renewed investment in communication infrastructure capable of interstellar distances. Long-term space colonization planning would receive increased priority, because knowing that interstellar travel is possible makes humanity's eventual expansion beyond Earth seem less like distant speculation and more like strategic necessity. These adjustments wouldn't be panic-driven. They would be strategic responses to changed understanding of what's possible in the universe we inhabit. They would represent humanity taking its place as a potentially spacefaring civilization rather than a species confined indefinitely to a single planet. The reason for exploring these implications isn't to convince you they're likely. It's to demonstrate that even unlikely possibilities can be examined rationally, that speculation doesn't require abandoning critical thinking, and that the most interesting questions often live in the space between certain knowledge and complete ignorance. In 45 days, on December 19, 2025, telescopes around the world and instruments in space will converge their attention on a single object moving through our solar system. 3i Atlas, at closest approach to Earth, maximum observability, optimal data gathering window. This is when speculation transitions to measurement, when competing models face empirical testing, when we get our clearest look at this visitor from beyond our solar system. Let me walk you through exactly what will happen and what it means. NASA's Deep Space Network will conduct precision tracking using radio telescopes at 3 locations strategically distributed around Earth Goldstone in California, Madrid in Spain, and Canberra in Australia. This triangulation network allows continuous observation as Earth rotates, ensuring no gaps in data collection. Radio signals will be transmitted toward 3i Atlas, measuring the reflected return time and analyzing Doppler shifts in frequency that reveal precise velocity and acceleration. This technique can determine the object's position with accuracy measured in single kilometers across distances of hundreds of millions of miles. If the object's observed position matches the position predicted by gravitational models, plus standard outgassing estimates, the natural comet hypothesis is confirmed. If the position deviates from prediction in specific, consistent directions beyond measurement uncertainty, that indicates acceleration components that our current models don't fully account for. Every kilometre of deviation becomes quantified evidence requiring explanation. The James Webb Space Telescope, assuming observation scheduling permits and no higher priority targets preempt the allocated time, will conduct high-resolution spectroscopic analysis. This technique splits light into its component wavelengths, revealing which elements and molecules are present based on which specific wavelengths are absorbed or emitted. By analysing light from 3i Atlas with extreme precision, astronomers can determine the carbon-to-oxygen ratios that provide clues about formation environment, the velocity vectors of outgassing that show which surface regions are sublimating most actively, the temperature profiles across different regions that indicate heating distribution, and any unexpected spectral features that don't match standard comet composition. This spectroscopic data answers the central question driving current debate. Where is outgassing actually occurring, and do those locations correlate properly with the observed acceleration directions? If the comet shows strongest outgassing activity from sun-facing regions that recently experienced maximum solar heating, and if the resulting acceleration vectors point in directions consistent with gas jets from those regions, then the outgassing model is confirmed, mystery resolved, natural phenomenon understood. If spectroscopy reveals outgassing from unexpected regions, or if acceleration vectors point in directions that don't align with observed gas release, even after sophisticated modelling, then we've confirmed a genuine anomaly that standard comet physics doesn't adequately explain. The Hubble Space Telescope will contribute visual wavelength observations, tracking any changes in brightness that might indicate increased or decreased activity, monitoring the structure of the coma, the cloud of gas and dust surrounding the nucleus for asymmetries or evolution that would indicate directional outgassing, and watching for any evidence of fragmentation or structural changes that would fundamentally alter our understanding of what this object is. Ground-based observatories across 6 continents will coordinate their observations, providing redundancy that eliminates weather-dependent failures at any single site, offering multiple independent measurements that can be cross-validated to eliminate instrument errors, and contributing diverse data from facilities with different capabilities and specializations. This distributed network means that December 19th observations don't depend on any single telescope or institution. The data will come from dozens of independent sources that would all need to be wrong in the same way for conclusions to be mistaken. The European Space Agency will contribute historical comparative data from missions like Giotto that flew past Halley's Comet and provided detailed in situ measurements of cometary structure and activity. This historical data provides a baseline for what typical comet behavior looks like under various conditions, allowing researchers to identify whether 3I Atlas's characteristics fall within normal ranges or represent genuine outliers. The single most critical measurement is simple. Does 3I Atlas arrive at the predicted position at the predicted time? NASA's orbital model predicts arrival at specific coordinates with precision of approximately plus or minus 5,000 kilometers. That sounds like a large uncertainty until you realize it's across a distance of 269 million kilometers, an accuracy of about 0.002%. If the object appears at that predicted position within measurement precision, it's following the calculated trajectory. Natural physics confirmed. If deviation occurs consistently beyond measurement error, particularly if that deviation shows directional patterns rather than random scatter, then alternative explanations are required. The precision of orbital mechanics cannot be overstated. The mathematics of gravitational interaction have been refined for centuries. We know where objects should be if only gravity and well-understood outgassing are affecting them. December the 19th tells us whether our understanding matches reality in this specific case, and that test has only 2 possible outcomes: confirmation or falsification of current models. Within hours of closest approach, preliminary data will be released to research communities. Within days, observatories will publish initial findings and raw data for independent analysis. Within weeks, coordinated analysis integrating observations from multiple facilities will produce comprehensive conclusions. Within months, peer-reviewed papers will present detailed methodology and findings to the broader scientific community. This entire process will be transparent, documented, and subject to independent verification. This is how science operates when it's functioning properly, not through institutional decree or hidden knowledge, but through open data and competitive analysis, where the best interpretation of evidence wins through demonstrable accuracy. December 19th isn't testing whether impact is possible. Orbital mechanics already conclusively ruled that out. It's testing whether outgassing explains the observed acceleration, whether interstellar comets follow the same physics as solar system comets, whether our planetary science models are complete or require refinement, whether we understand these visitors as well as we think we do. All legitimate questions, all answered through observation, all contributing to human knowledge regardless of which answer proves correct. Let me close this investigation by discussing something that often gets overlooked in conversations about frontier science: how to think productively when facing genuine uncertainty. Because that's what 3I Atlas fundamentally represents: a situation where we have substantial data, multiple plausible interpretations, and insufficient evidence to reach definitive conclusions. That's not institutional failure. That's not conspiracy or cover-up. That's simply the current state of knowledge about a complex phenomenon, and understanding how to navigate that ambiguity is crucial for thinking clearly about any scientific question. There's a trap people fall into called false equivalence, where all positions are treated as equally valid simply because multiple viewpoints exist. You hear it phrased as some scientists say it's natural, some say it might be artificial, so who really knows? But that framing misrepresents the evidential landscape. The outgassing hypothesis has decades of precedent, extensive observational support, well-developed theoretical frameworks, and consistency with established physics. The intentional guidance hypothesis has some observational anomalies that don't fit standard models perfectly, but far less supporting evidence and no clear mechanism. These aren't equivalent positions. One is substantially more likely given current evidence, but substantially more likely isn't the same as certain, and less likely isn't the same as impossible. Both remain within the range of possibilities that evidence permits, just with different probabilities. The opposite trap is reflexive skepticism, where anything unusual gets dismissed without investigation, simply because it seems extraordinary, or because accepting it would require changing assumptions. You hear this as, "It's probably just outgassing, these anomalies don't matter, no need to investigate further." But that's anti-scientific. Science advances precisely by investigating things that don't fit existing models. That's literally the mechanism of discovery. Healthy skepticism says, this is probably explainable through known physics, but let's investigate the anomalies carefully to be certain. Reflexive skepticism says, this must be explainable through known physics, so the anomalies can be ignored. One stance investigates, the other dismisses. One discovers new phenomena, the other reinforces existing beliefs regardless of evidence. The intellectually honest position acknowledges complexity. Available evidence most strongly supports the outgassing hypothesis, which is where institutional science reasonably focuses primary attention and resources. But certain observational features don't fit that model perfectly, even after sophisticated analysis, and those features deserve continued investigation rather than dismissal. Alternative explanations remain unlikely, but not impossible given current data. Upcoming observations will test which interpretation better matches reality. Until those tests occur, maintaining informed curiosity about multiple possibilities is more scientifically appropriate than premature certainty about any single explanation. When you encounter claims about 3i Atlas or any complex scientific topic, evaluate them systematically. Ask who is making the claim. Named researchers with relevant credentials publishing in peer-reviewed venues carry more evidential weight than anonymous social media posts or unverified forum claims. Ask what evidence supports the claim. Direct observational data constitutes strong evidence. Mathematical calculations with transparent methodology constitute moderate evidence. Appeals to authority without underlying data constitute weak evidence. Circular reasoning where claims reference only other claims without grounding in observation constitutes no valid evidence. Ask whether anyone has attempted to falsify the claim. Good science makes predictions that could potentially be proven wrong. If no possible observation could falsify a claim, it's not scientific hypothesis, it's unfalsifiable belief. Apply this framework specifically to 3i Atlas claims. The outgassing hypothesis comes from credible institutional sources like NASA and ESA, is supported by strong historical and observational evidence, makes falsifiable predictions about December 19th observations, and deserves high confidence while acknowledging it's not absolutely proven. The intentional trajectory hypothesis comes from credible but controversial researchers like Avi Loeb, is supported by moderate-strength evidence in the form of anomalous acceleration patterns, makes falsifiable predictions that December 19th will test, and deserves low to moderate confidence as a possibility worth investigating. The signal detection claims circulating on social media come from unverified sources, lack institutional confirmation despite having ample opportunity to be verified, make extraordinary claims without extraordinary evidence, and deserve very low confidence bordering on dismissal. Science feels frustrating when it doesn't provide immediate definitive answers. We want certainty. We want resolution. We want to know conclusively whether 3i Atlas is natural or something else. Ambiguity creates cognitive discomfort. But ambiguity, where evidence genuinely permits multiple interpretations, isn't a failure of scientific methodology. It's an accurate representation of the current state of knowledge. The scientific method handles this perfectly through hypothesis generation, careful observation, and comparison of predictions to measured reality. If evidence initially supports multiple explanations, you design observations that can distinguish between them. That's not confusion. That's the precision of not claiming to know more than evidence supports. December 19th provides exactly that distinguishing observation for 3i Atlas. Until then, acknowledging we don't yet know with certainty is more intellectually honest than false confidence in either direction. Your responsibility as a consumer of scientific information is to ask critical questions. Is this source claiming certainty beyond what evidence supports? Is this analysis dismissing legitimate questions without proper investigation? Is this narrative using fear or excitement to bypass critical thinking? Is this claim presenting unverified speculation as established fact? Does this presentation acknowledge uncertainty appropriately where uncertainty genuinely exists? If your answers concern you, that content is probably prioritizing engagement metrics over accuracy. Science advances when audiences think critically about sources, evidence and reasoning rather than simply accepting whatever narrative feels most compelling or aligns with existing beliefs. We're standing at the edge of an answer. 45 days separate us from the moment when 3i Atlas reaches its closest approach to Earth, when speculation faces measurement, when competing hypotheses confront observational testing. The questions we've explored throughout this investigation, natural comet following understood physics, or anomalous behavior requiring new explanations, are about to receive substantially clearer data than we currently possess. This isn't prediction. This isn't prophecy. This isn't fear-mongering about catastrophes that orbital mechanics already ruled impossible. This is observational science approaching a critical data point. Multiple institutions, thousands of researchers, millions of measurements, and a moment when evidence either confirms our understanding or reveals gaps requiring new investigation. What happens on December 19th isn't the conclusion of inquiry. It's a milestone. It's measurement. It's a test where results might confirm existing models, might require refinement of those models, or might reveal entirely unexpected characteristics that generate new questions we haven't yet considered. That's how the scientific process functions. That's how humanity gradually learns about the cosmos we inhabit. That's how we progressed from thinking Earth was the center of everything to understanding we're part of a vast universe we're only beginning to comprehend. 3i Atlas will pass at its closest point. Instruments will gather data, researchers will analyze findings, scientific communities will debate interpretations, and we'll understand interstellar visitors incrementally better than we did before. That's the actual story, not conspiracy, not hidden threats, but the patient accumulation of knowledge through careful observation. But here's what I want you to remember as December 19th approaches. This investigation doesn't end when this video ends. The story continues as new observational data emerges over the next 45 days. The story continues as preliminary findings are published. The story continues as you engage with evidence and form your own reasoned conclusions. You can be part of this process, not as passive audience consuming entertainment, but as active participant thinking critically about real scientific questions unfolding in real time. Science isn't something that happens to you. It's something you engage with through curiosity, through critical evaluation of claims and evidence, through willingness to hold multiple possibilities simultaneously until data distinguishes between them. 3i Atlas provides an opportunity for exactly that kind of engagement. A real astronomical object, real observational data, real scientific debate, real opportunity to practice scientific thinking about genuine uncertainty. Over the next 45 days, I'll be tracking new data as observatories release it. I'll be analysing preliminary findings as they emerge. I'll be examining peer-reviewed papers as the scientific community processes observations collectively. And I want you involved in that process, not as passive consumers but as fellow investigators, discussing findings in comments, sharing interpretations, engaging critically with claims you encounter, building community around rigorous inquiry rather than around any particular predetermined conclusion. That kind of community is where good science flourishes. That's where curiosity meets intellectual discipline. That's where frontier questions get explored responsibly, without abandoning critical thinking. Here's my final thought. 3i Atlas represents something profound about human progress. For most of our species' history, we couldn't see beyond our immediate surroundings. Now, we can detect objects from other star systems. We can measure their properties across hundreds of millions of miles. We can ask meaningful questions about their composition, their origins, their behavior. We can test hypotheses through observation. We can distinguish between what we know, what we don't know, and what we might learn through investigation. That's extraordinary. Not because aliens are probably visiting, which current evidence doesn't support, but because our understanding has expanded so dramatically, because we've developed instruments and methodologies allowing us to study visitors from beyond our solar system, because we can examine something that travelled unimaginable distances and ask rigorous questions about what it is and what its presence means. December the 19th, 2025 is when one chapter of this investigation reaches a crucial data point. when speculation transitions to measurement, when models face empirical testing, when the universe provides clearer answers about itself through careful observation. I hope you'll be following along as that date approaches. I hope you'll be thinking critically about what observations reveal. I hope you'll be engaging with the science rather than just the sensationalism. Because that's where the genuine story lives, not in viral claims or conspiracy theories, but in the patient, rigorous work of humans trying to understand a cosmos far larger and stranger than ourselves. Thank you for investigating with me. Thank you for thinking critically about sources and evidence. Thank you for maintaining both curiosity and skepticism. Thank you for being the kind of audience that makes good science communication possible. December 19th awaits. The data will arrive, and we'll understand a little more about these mysterious visitors from beyond our solar system. Stay curious. Stay critical. Stay engaged with what's actually happening rather than what fear or wishful thinking might prefer. The universe has more to teach us, and the next 45 days are part of that ongoing education.